This video is for number 46 of section 8.4. An Atwood's machine consists of blocks of masses M1 equal to 10 kilograms and M2 equal to 20 kilograms attached by a cord running over a pulley as in the figure below. So M1 is 10 kilograms and M2 is 20 kilograms. The pulley is a solid cylinder with a mass of 8 kilograms and a radius of 0.2 meters. The block of mass 2 is allowed to drop and the cord turns the pulley without slipping. So what's happening is you have the system at rest and you have two masses hanging on either side of the pulley. And because these masses have weights going downward, the tension would act on the string upward, T1 and T2. And then when the system is released, M2 is allowed to drop downward, so you accelerate in the downward direction on the right hand side. And because they're on a string and mass 2 is falling downward, M1 will be accelerating upward. So part A of the question asks us, why must the tension T2 be greater than the tension T1? So the system is accelerating downward to the right, and we know that because it's rotating around the pulley that there must be torque involved. So both T1 and T2 cause torque. They're a perpendicular force, that would be right here, and they are a distance r away, that would be their lever arm, so they both cause torque. And the system begins at rest and then accelerates this way. So you have an angular acceleration that is clockwise, and that is caused by the combination of the torques. But if the angular acceleration is clockwise, then we know that T2 has to be greater than T1 because the angular acceleration should be in the direction of the net torque. Which is clockwise. Part B, what is the acceleration of the system? Assuming the pulley axis is frictionless. So we're looking for the acceleration A. And to do so first, we can sum our torques. So our net torque is equal to the torque from tension 1 plus the torque from tension 2. And recall the torque equation is the perpendicular force times the lever arm. So our torque then looks like T1 times the radius r, and that causes a counterclockwise torque, so it's positive, but minus the clockwise torque caused by T2 at a radius r. Okay. We can then move into our next equation that torque is equal to the moment of inertia times the angular acceleration alpha, but in this case we'll need a negative right here in this equation because the angular acceleration is clockwise, and clockwise is the negative direction. And we also know that the moment of inertia for the pulley, because it is a solid cylinder, we use the equation 1/2 mass of the pulley times the radius squared. So now we can put these equations together. So we have the torque on one side, so the net torque, which is this equation, I'm putting that in right here, so have T1R minus T2R. Is equal to the negative moment of inertia times the angular acceleration. The moment of inertia is equal to 1/2 mr squared. That's the mass of the pulley for that end. And then times the angular acceleration alpha. We can cross out these r's, and that brings us to T1 minus T2 is equal to negative 1/2 the mass times the radius times alpha. But we are not looking for the angular acceleration, we're looking for the linear acceleration. So we need the equation A is equal to R alpha. We can put that in for alpha. So T1 minus T2 is equal to negative 1/2 m r times A times A over R. These r's cancel out, so we have T1 minus T2 is equal to negative 1/2 the mass times the acceleration. And to get rid of this negative, I'm just going to multiply it to the other side and then flip the order of that subtraction. Okay, so we can now apply Newton's second law to each of the masses, of the hanging masses that are accelerating. So we should remind ourselves of Newton's second law. The sum of the forces is equal to the mass times the acceleration. And we can do mass 1 first. So we can say that anything in the direction of the acceleration is positive. So T1 minus, it has a weight going down, m1g is equal to m1 times the acceleration and to help us out, it might be helpful to solve for T1. We can have T1 is equal to m1a plus m1g. We do the same for the second mass. So T2 actually would be, the acceleration is downward, so we would have anything in the positive direction is downward. M2g, and then minus T2 is equal to M2a. So T2 is equal to M2g minus M2a. And then using this equation, we can substitute T1 and T2 in, and then solve for A. Just going to distribute that negative. And then get all of the A's on the same side. On the left, I'm going to leave it the same, and on the right, I'm going to factor out the A and then divide. So when we solve for A, we're left with the weight of mass 1, or minus weight of mass 2 minus the weight of mass 1 over 1/2 times the mass of the pulley plus mass 1 plus mass 2. And then putting in our numbers, and then when you do this math, you'll get an acceleration of 2.88 meters per second squared. Part C of the problem asks us to solve for the tension in T1 and T2, and now that we know the acceleration, we are able to do that. So we can use this equation to solve for T1. T1 is equal to mass 1, so 10 kilograms times 2.88 meters per second squared plus 10 kilograms times 9.8 meters per second squared. So T1 comes out to be 126.8 newtons. Now that we know T1 and A, we can easily solve for T2. And I'm going to use this equation at the top. T2 is equal to 1/2 the mass times the acceleration plus T1. So that's the mass of the pulley, which is 8 kilograms, times the acceleration, 2.88 meters per second squared, and then plus 126.8 newtons, which we just found for T1. And for T2, we get a value of 138.32 newtons. And this makes sense because in part A, we said that T2 had to be greater than T1 to cause the torque in the clockwise direction.